Euler's reflection formula for dilogarithms. Okay, so basically you might have seen reflection formulas for gamma function, digamma functions. Yeah, basically for gamma function, that is gamma x, gamma 1 minus x, its product is actually equals to pi by sine pi x. Yeah. Similarly, for digamma function, you might have seen that digamma of 1 minus x minus digamma of x, this is pi by tan pi x. Might have seen such formulas. So a similar formula exists for dilogarithm as well. And the dilogarithm's reflection formula is basically if you have dilogarithm of x plus dilogarithm of 1 minus x, this is actually equals to Riemann zeta of 2, which is pi square by 6 minus ln x ln 1 minus x. Now, when is it helpful? So basically, if you have to find, let's say, li2 of 1 by 2, in that case you can substitute x as 1 by 2 and get the result that this is actually equals to zeta of 2 minus ln square 1 by 2 by 2. Similarly, let's say if you have to find dilogarithm of 1 by 4 plus dilogarithm of 3 by 4, you can again use the same identity to find the sum, and that will be zeta of 2 minus ln 1 by 4 ln 3 by 4. Yeah, so these are some of its uses. Now let's go to the proof. If you don't know about dilogarithms, like I will basically give a brief introduction, and I think that will be enough for the video. So basically, Poyle logarithm function is defined as sum going from n equals to 1 to infinity of g to the power n by n to the power s. Now if s is 2, this is actually equals to sum going from n equals to 1 to infinity of g to the power n by n square. Now this sum is also equals to an integral, which is integral from 0 to g minus ln of 1 minus t by t dt. So this integral is basically a new definition for dilogarithm function, and that will be the one that we will use in this video. Okay, let's proceed to the video now. So we basically have to find this sum, dilogarithm of z plus dilogarithm of 1 minus z. Yeah. If we use the integral representation for dilogarithms, we will get this as integral from 0 to g of minus ln of 1 minus t by t dt. Yeah, and over here we will get integral from 0 to 1 minus g of minus ln of 1 minus t by t dt. Now you might want to simplify the limits of integral. For that, what you can do is you can basically replace 1 minus t by y. That will also take this to g. Okay, so now basically after we have y, we can again write y as t again, because that's just a dummy variable. Basically, so I can write this as t goes to 1 minus t, but let me do it as it is for now. So minus ln 1 minus t by t dt. Now with this substitution, the lower limit will be 1 and the upper limit will be 1 minus 1 minus z, that's just g. Now this is minus ln of g. Now we have, oh sorry, not g, y by, now this is just 1 minus y, and over here I have minus dy. Now let me write y as t again, doesn't matter because I can write y as anything, because that doesn't really matter, and that's some dummy variable. T by 1 minus t minus dt. Basically the dt, if here's like d alpha and here's just alpha, the integral will be the same, that doesn't really matter, that's why. Now we have this thing. Now if we to be able to integrate this, we basically have to have ln 1 minus t by t, yeah, but this is in the opposite form. That's why what I can do is differentiate numerator, integrate denominator, for which you can use integration by parts. If we use integration by parts, we will be able to use that thing. That's why what I can do is we can basically use integration by parts. That gives us ln t, and the integral is ln 1 minus t by minus 1 minus integral from 1 to z. Now derivative is 1 by t, integral is ln 1 minus t by minus 1 and then dt. Now minus 1 cancels out and this becomes plus. Okay, Now, and this should be evaluated at 1 to z. Yeah. Now note that at 1, this is ln of 1 into ln of 0, which is 0 times infinity. So you have to take limit. And if you just try the limit using series expansion of ln 1 minus t, you will see that that's actually 0. Now let's do this. So we have 0 to z minus ln of 1 minus t by t dt. Over here I have integral from 1 to z ln of 1 minus t by t dt. Okay, and now over here what do we have? We have plus. Okay, so there's minus 1, so that's why minus ln of z ln of 1 minus z, and then plus, we know that at 1 by limit we can I have the answer as 0. Now over here, so basically over here, if we make a minus sign over here and take also a minus sign over here, now we can basically see that both of these are integrals of minus ln 1 minus t by t, minus ln 1 minus t by t. We are subtracting over here, the limit is from 0 to z, over here it's from 1 to z. Subtracting 1 to z from 0 to z, we get integral from 0 to 1 of minus ln 1 minus t by t dt. Yeah. Now it's really simple. Let me write in proper handwriting. Now this one is really simple. Yeah, I think you might have guessed now how will we solve. Over here we have minus ln of z ln of 1 minus z. Yeah. Now after this, this is basically the definition for dilogarithm function, and over here it's 1, so that's why it will be dilogarithm of 1 minus ln of z ln 1 minus z. Now to find dilogarithm of 1, we will use the series expansion formula. So this will be sum from n equals to 1 to infinity. Our x is 1, so 1 to the power 2. Sorry, is that? Okay, so 1 to the power, not 2, 1 to the power n. 1 to the power n by n square minus ln of z ln of 1 minus z. Now ln 1 to the power n is just 1, so this is sum of 1 by n square, which is zeta of 2 minus ln g ln 1 minus c, and we proved the reflection formula. Yeah, so basically the proof was not that hard. So basically we had to use the integral definition of dilogarithm function, and then make some u substitutions to simplify the limits of integral, and then use integration by parts to get a standard form for the integral that we can use, and then and then some property of integrations, and over here a good limit problem, and we got the solution. So this was the proof, and hope you understood the solution I did, and hope you are also applying this formula for different dilogarithms arithmetic problems. And yeah, that was it. Hope you enjoyed the video, and look forward to seeing in the upcoming videos too in this playlist, like where I'm basically proving other identities, like let's say inversion formula of dilogarithms. Yeah, if you don't know about the inversion formula, so this is basically li2 of z plus li2 of 1 by z. This is actually equal to minus Riemann zeta of 2 minus 1 by 2 log square of minus c, and there's an other formula too. Yeah, also known as Landens identity. So yeah, there are other formulas too. Do check the playlist for upcoming videos. Yeah, that was what I want to say.